Hey guys, let's take some time to run through the notes for our next section 10.3, which is on properties of chords. Now we already defined chords back in section 10.1, but just to review a little bit, what you need to remember is that it's always going to be a segment, which means it has endpoints, and those endpoints are always going to lie on the circle, as you can see in this picture on the right with this chord. All right. The other thing you need to remember is that if a chord is a diameter, it's going to create a semicircle. All right. So a diameter is just a special case where the chord is running through the center of my circle. So in this picture on the right, it's creating a semicircle up above and obviously a semicircle down below. Because what I'm doing is splitting the entire circle 360 degrees into two separate parts. Now, any other chord I'm drawing that's not a diameter, like the picture on the right over here, all right, what's going to happen is I'm just going to split my circle into two arcs, one of them obviously being a major arc, more than a semicircle, and one being a minor arc, anything less than a semicircle. Now, the first theorem I come across in this section deals directly with chords, obviously. And what it's talking about is not only congruent minor arcs, but also congruent chords. So if we look closer at this picture they have on the right, what they're saying is that chord BA is obviously congruent to chord CD. And what that means is that arc BA, however big it is, let's say in this case, I don't know, it's 110 degrees, it's going to mean that arc CA over here on the right is obviously also 110 degrees. Now, the thing is, this theorem works in reverse as well. If I'm given the two arcs that are both 110 degrees on the left and the right, BA and CD, I automatically know that those two chords have to be congruent because the arc measures were congruent. All right, and the way I know this works both ways is stated right here back in the theorem, where it says if and only if. All right. So in my first example, this picture on the right with circle D, I'm told that arc AB is 110 degrees. And what I want to figure out is the measure of arc BC. Well, if you notice, the chord BA that forms that arc is 9. And this chord BC is also 9, which obviously is going to tell me that arc AB is congruent to arc BC, the theorem that we just reviewed. Now the next example they give me is slightly different because the arc measure they're giving me is AC, on the outside of those two chords. What they're telling me is AC is 150 degrees. What I'm looking for is the measure of arc AB. Now, you have to look at the other information given. I know that chord AB is congruent to chord BC, which tells me that arc AB is congruent to arc BC. Well, once again, I know that it's 360 degrees all the way around my circle. All right, well, if I take out the one arc that I do have, that 150, that's going to leave me with 210. Now, in this case, I don't need all of that 210. It's split evenly between arc AB and arc BC. So what I'm going to do is cut that in half, which leaves me with 105 for my final answer. For this next example, what they want to know is the length of AB. So if I look at what's given in my picture, I have 155 for arc AB, and I also have 155 for arc CD. Now, since these two arcs are congruent, 155 and 155, that tells me that these chords that open up to them must also be congruent. So obviously AB is going to equal 9. For this next problem, I want to focus on the same information that's given. All right, what they're trying to show me is that this piece, KJ, is congruent to this piece, LM. Now, in this case, the chords I'm focused on would obviously be this one, LJ, and KM. Now, obviously, LJ is 8 in total. All right, well, the problem is LJ opens up to this entire arc. Well, the thing is, this piece, JM, is shared by both this arc and this arc. So in that case, if I put this green arc with JK instead, it's going to be the same length as if I put it with LM to the right, which tells me that this arc must have this corresponding chord with a length of 8. Last problem from this section, they're looking for an arc measure. So they want to know TU. Well, the information I'm given is that chord SR is congruent to chord TU. The other piece of information I know is that this central angle right in here is 85 degrees as marked, which tells me that this arc must also be 85 degrees. Now, there's two ways to go about this. Since I know these chords are congruent, then I know that this obviously has to be 85 degrees. The other way to think about it is if I extend these segments to these other points, essentially drawing diameters across my circle, all right, what I've formed in the center here are vertical angles, which tells me this center angle is 85, this center angle is 85. This arc is 85, so this arc is 85. The next two theorems from the notes go hand in hand. We have the perpendicular chord bisector theorem, followed by the converse. Now, the perpendicular bisector theorem starts with the diameter of my circle. So we have EG, the diameter, and I know it's the diameter because it's going through the center of my circle. And the thing is that it's perpendicular to a chord. So here's my chord, FD, and they've marked that it's perpendicular because I have the right angle right here. Now, the other thing is that it bisects that chord. So it cuts FD right in half. So therefore I know that FH is going to be equal in length to HD. Now, the other thing they mention is that it also bisects the chord. So I could also say that chord FG and chord GD are congruent. Now, as far as the converse goes, now I'm just working in reverse. First thing I'm starting with is the chord in my circle. So now in this case, I'm starting with TR. And I'm already told that it's perpendicular, so it has the right angle. And I'm told that it bisects, which tells me that these two pieces are congruent, and obviously the two arcs are going to be congruent out here. Now, if it's both perpendicular and a bisector, as it states, then the other chord in my picture, in this case SQ, must go through the center of my circle, which means that it is the diameter. So for the first theorem, I start with the diameter, and I'm led to the chord that's bisected and the arc that's bisected. For the converse, I'm starting with the chord. All right, the chord that's bisected and perpendicular, and I'm finishing with the diameter. Now, for these next couple examples, I'm focused on this picture. As I said before, just focus on everything that you're given in the picture. I know that BD is a diameter. Obviously, it's perpendicular to this chord, which tells me, based on the theorem up above, that CF is 5 and FE must also be 5 because it's bisected. Now, in addition to that, as I said, since this chord is bisected, that means that this arc is also congruent to this arc. So, right away I can set up an equation. I know that if arc CD is congruent to arc DE, then I know that 9x equals 80 minus x, which leads me to 10x, which equals 80, which tells me that x equals 8. And if x is 8, that means that arc CD is 72 and arc DE is 72. So based on all that, I should be able to go back and actually answer the questions that they're asking. First one they wanted was CE. Well, in my picture, we got 5 and 5, which tells me CE is going to be 10. And the measure of arc CE, which includes arc CD and arc DE, 72 and 72, which gives me 144. So for these next couple of examples, what they want to know is segment QS, a diameter of circle C. So they want to know, does this chord right here pass through point C, the center of my circle? Well, we have to look at everything else that's given. First thing I notice is that these two are congruent, which tells me that this chord right here is cut in half. In other words, bisected. Now, the other thing I notice is that this right here is perpendicular. So that means that if QS is a perpendicular bisector for chord PR, then it must be the diameter based on my theorem. Next problem, same question. Is QS the diameter? Does it pass through the center of my circle? Well, I noticed right away that it is perpendicular to chord PR. Now, the other thing that needs to be true is that it must bisect chord PR. Well, if you notice, the left side is 19 while the right side is 20. So they are actually not congruent. So in this case, the answer is no for that reason. Now, this last problem is asking the same question, but it's slightly different. Okay, they didn't mark directly that these were congruent, but obviously they are, because it's 9 and 9. So I know that that chord is bisected. But it has to be perpendicular to this chord. Well, if I look closely at the way that they marked it, I know that this angle and this angle are congruent. So what I have is two adjacent angles that form a straight angle, that are congruent. So these two together are going to add up to 180. They both have the same measurement, which tells me that they must be 90 and 90. So even though it isn't marked that way in my picture, I know that I can put that little perpendicular marking at their intersection. So therefore my final answer is yes, because it is perpendicular and it is a bisector. Now for the last theorem in this section, the equidistant chords theorem, once again I notice that it has that statement if and only if in it, which means that it's going to work both ways. So what they're saying is that in the same circle, or congruent circles, two chords are congruent. So it looks like the two chords they're referring to in this picture would be AB and CD. So if those two chords are congruent, all right, then they must be equidistant from the center. So which means these little segments coming off my center, point E, are the same length. Well, let's take a closer look at this picture. So the way they present the theorem is they state that these chords AB and CD are congruent. Now, if those chords are congruent, then they must be the same length from the center. And notice that the way they measure the length from the center is that it's perpendicular to the chords. All right, so they're not measuring the distance from the center to the chord with a segment like this or like this. Okay, it has to be perpendicular to the chord. Now, as I said, since it contains that statement if and only if, it could work in reverse. So in other words, if I start with the fact that they are the same distance from the center, then these chords AB and CD must be congruent. Now, this builds on my theorem from earlier in the section. If these two chords are congruent, AB and CD, what that tells me is that these arcs, CD and AB, are congruent. And that's going to be important for the next couple problems. Now, for this next problem, what I'm looking for is the length of segment AQ. This piece right here. There's a lot going on in this picture. So, first thing I notice is that chord DE right here is 18, and chord GF down here is 18. Now, as I stated above in that theorem, since these two chords are congruent, 18 and 18, they must be equidistant from the center of my circle, from point Q. So these two segments in red, they're perpendicular to the chords. So they're telling me that's the distance from the chord to the center of my circle. And this one up above is 7, C to Q. So that means A to Q must also be 7. For this next example, I'm looking for HJ. So I'm looking for the length of this chord over here on the left. Now, if you notice, the distance from the center to that chord is 4. Well, the distance from the center to this chord on the right is also 4. And this chord on the right is 7, which tells me that JH must be 7. And for the last problem in the set, now I'm looking for an arc measure. So I'm worried about the measure of this arc right here, M to N. Now, first thing I notice is these are bisected. All right, and it's perpendicular, which means even though this is marked, I know right away it has to be the diameter of my circle. Now, since it's the diameter, that means that this piece must be a semicircle. So that whole arc is going to add up to 180. Well, they've already told me that this piece down here is 130, which means that this side, arc PM, is going to be 50. Now, from the theorem we talked about earlier, because this is a perpendicular bisector for this chord, it means that these arcs are also going to be congruent. So PM is 50, which means that NP is 50. So my final answer for MN is going to be 100, since both those arcs are 50. The next couple problems are a little bit more involved. Now they actually want me to solve for x. So in this problem, the first thing I notice is that from the center of my circle to these two chords, that distance is the same, 18 and 18, which tells me, based on the theorem we mentioned earlier, the equidistant chords theorem, that these two chords, ST and VU, must be equal in length. Since they're equal, I'm going to take their two expressions, 6x minus 5 and 13 plus 4x, set them equal to each other. So we end up with 2x equals 18, so x equals 9. For this next problem, I'm also trying to solve for x. Now the picture looks similar to the last one. They give me this segment, which is a diameter. It's going through the center of my circle, point J, and it is perpendicular to this chord that it's intersecting. So based on that, I know from earlier that since that diameter's perpendicular to that chord, that the perpendicular chord bisector theorem tells me that it has to be cut in half. All right. So immediately I know that 3x plus 16 is going to be equal to 12x plus 7. Then we can solve from there. So it looks like I end up with 9x equals 9, so obviously x equals 1. Now the last two problems from this section are definitely the hardest ones. The first thing they're asking for is the length of BD. So I want to know the length of this chord right here. So I'm given certain pieces of information in my picture. Now the 4 right here is just for this short segment, C to E. And then the 6 that I'm given down here is for A to E. Now, a couple things I notice is that it's perpendicular to this chord. All right, well, based on my theorem from earlier, all right, the perpendicular chord bisector theorem, I know right away that since it's perpendicular, it must be bisecting this chord, all right? And it has to be true because this is a radius, all right? So it's part of the entire diameter of my circle. Okay, so I know that both of these sides are going to be congruent. Now, if I can solve for one of them, obviously I can double it and I'll get the full length of BD. Now, in this picture, they specifically point out this piece right here, this dashed line. Now, I know, based on earlier, that that part of the circle is my radius. Right? Well, I know the length of the radius of my circle because AC is a radius. The length of the radius is going to be 6 and 4, which gives me 10. So now I know that this piece on the left is 10. So what I want to focus on is finding this piece. Well, now let's just focus on this right here. Okay, so I have this right triangle, and I have 2 out of 3 sides, 6 and 10. So this is what I have, a right triangle. The hypotenuse is 10, one of the legs is 6, and obviously I'm just looking for the other leg. So I can set up my Pythagorean theorem to solve for that third leg. And it looks like that third leg is going to be 8. Now, if you didn't notice earlier, this is actually my 3, 4, 5. So you might have just jumped to the conclusion that that third leg had to be 8. So if I go back to my picture, now I know that from B to E is 8. Well, what they're looking for is B to D. As I stated earlier, these two segments are congruent, so B to D is going to be 16. So for this last problem, they don't have anything marked in my picture. What I'm told is that RS, this short segment right here, is 8, and that HJ this whole chord over here on the right is 30. Then, what I'm looking for is the length of the diameter, but I'm going to need to fill in more information in my picture. Now, as I stated in the last problem, based on the perpendicular chord bisector theorem, since this right here is perpendicular to this chord, I know right away that it has to bisect it. So I can split that 30 up into 15 and 15 for each of those shorter segments. All right, now, how's that going to help me? Well, if I want the diameter, if I want the full length all the way across my circle, it would help if I knew the length of the radius. All right, well, I know part of it's going to be 8, but I don't know the whole thing. So, instead of focusing on this radius that I've highlighted, RT, let's draw another radius. How about this one? If it'll stay. So, now what I have here is a right triangle. All right, and let's draw it bigger off to. So for this right triangle, I can fill in the side lengths that I do have. So I know R to S is going to be 8. I know that H to S is going to be 15. And what I'm looking for is R to H, which, as I stated earlier, is actually the radius of my circle. All right, well, in this case, I have both legs. I'm looking for the hypotenuse, so I can set up my Pythagorean theorem. Now, you might notice right away that this is actually also one of my triples. So I know, without having to go through all the work, that third side length is going to be 17. So I found R to H. I know it's going to be 17. And what they're actually asking for is the diameter. All right, well, I have the radius. And in this case, the diameter is just going to be double that, which gives me 34 for my final answer.